Mhm.
Okay, so the next speaker is Uli Fahrenberg. He is our local organizer of the now non-local conference, and he speaks about generating posets beyond N.
Yes. Let me just prepare my screen share. So can you see my screen?
Yes.
Okay, very good. So this is work together with Christian Johansson and Ratan Bahadur Thapa from Oslo University and Georg Struth from Sheffield University. And I should say behind the scenes, at least morally responsible for some of those things is also Krzysztof Ziemiański, who is in the audience. And so this is work on generating posets beyond N. So let me start with this N. What you see here is the poset N. Now, you might tell me this, it doesn't look like an N, it looks more like a Z. But this is because we work in concurrency theory. So this work situates itself within concurrency theory, within concurrent linear algebra. And there we think of the arrows in a poset as precedence orderings of events, right? So it's naturally for us to write posets from left to right. If you wish, you may see the N in its Hasse diagram version. So now you hopefully agree that this is an N, but for us, this is an N. We might not be very strong in the alphabet. So what is it about this N? Well, so we work in concurrent linear algebra because we find linear algebra nice and useful. I'm sure most of you agree that linear algebra is nice and useful for a lot of things. Also, its extensions to semi-modules and tests and domain. And we've seen some of this in Bernhard's talk just a minute ago. Concurrent linear algebra was introduced by Bernhard together with Tony Hoare, Peter O'Hearn, Georg Struth, and some other people in 2009. And so this extends linear algebra with a parallel composition, right? It's a version of an extension of linear algebra, which can be used in concurrency because you don't only have sequential composition, but also parallel composition of things. And now the free concurrent linear algebra, minus some details which I'm omitting, is the set of sets of series parallel pomsets. What are series parallel pomsets? Those are posets which are labeled and which are generated from the singleton poset using a finite number of concatenations and parallel compositions. And the point of our work is that the N you see again above is not a series parallel posets, but we would like it to be. So for us, some things are amiss in concurrent linear algebra. Here's an example using a formalism called higher dimensional automata. So what you see here are two commuting squares of actions. So on the left, you see a commuting square of AC and CA, right? So if you go first up and then right, you do first an A and then a C. Similarly, you can do first a C and then an A, but now the square in the middle is filled in, which means that A and C can actually run concurrently, right? So if the square was empty, then you would only have the choice between the two sequential executions, but as there is a filled-in square, it means A and C can run concurrently. Similarly, on the right, A and D can run concurrently, and below you see the pomset representations of those executions. So very simple pomsets, A in parallel with C, no special order included, and A in parallel with D. Now, in higher dimensional automata, we can concatenate those two squares to a rectangle, which you see on the right, which is now the two squares concatenated along the A transition. So what does it signify computationally? Well, it means that the A is running in parallel with C followed by D, right? So you have C first, well, you have C before D, and all the while A is running in parallel, and you see again the pomset representation of it below. Now we can do this composition in higher dimensional automata, but we can't do it in series parallel pomsets. So I mean, we can try. There are two operations in series parallel pomsets. There is parallel composition. What do you get as the parallel composition of AC and AD? Well, you get AC, AD all in parallel. This is not what we wanted. You can do serial composition of those two Posets. So AC serial AD. What does it become? Well, this just means now that you have two A actions. You have an A and a C in parallel, all in front of another A and a D in parallel. Right? So it's again not what we wanted. What we want is a composition operation on Posets, which allows us to continue events across compositions. So we want to have some star A composition you see there, which we call gluing, and which allows us to say that actually those two A's are the same thing, and they are continued across a composition. Here's another example, again using a higher dimensional automaton. Now here you see three squares which are concatenated first along the A transition and then along the D transition. And their corresponding gluing is indicated below. So what does it get you as a result? It gets you the Poset which has A in front of B, which has C before D, but also C before B. Right? And this is what you see as a computational interpretation of this higher dimensional automaton. Also, if you imagine that you start in the top, in the bottom left corner and you go to the top right corner, you will see that, okay, C is executed before D, A is executed before B, that's okay, but also B cannot start before C has finished because of the shape of the thing, right? So now you also see that this is the N Poset. Which means that we have found a higher dimensional automaton whose execution is the N Poset, which is not series parallel. So executions of higher dimensional automata go beyond series parallel Posets, which is the motivation for the title of our paper, Generating Posets Beyond N. So here is the paper. You've seen the introduction. I will talk a bit about series parallel Posets as a background, and then I will introduce the contributions of the paper, which are Posets with interfaces and gluing operation on them and gluing parallel Posets with interfaces. So let's get started with the series parallel Posets. What is a Poset? A Poset is a finite set plus a partial order. So the only interesting thing to notice here is that we only consider finite Posets in this work. Now on Posets, you have two compositions. You have parallel composition, which puts things on top of each other. So the carrier set of a parallel composition is the disjoint union of the two carrier sets, and the order is just the union of the two orders. And then you have serial composition, which puts things next to each other. Right? So you have P1 serial P2. The carrier set is again the disjoint union of the two carriers, and the order is, well, the order on the first one, union the order on the second one, union P1 before P2. Everything on the first Poset comes before anything in the second Poset. Here's an example, the serial composition of two ends. So you see on the right-hand side, you see the two ends, and in the middle, there are arrows from all the maximal events of the first Poset to all the minimal events of the second N. Okay, now series parallel Posets, you find them in papers by Winkowski in 77, Grabowski in 81. So those are Posets which are generated from the singleton by a finite number of serial and parallel compositions, or empty, right? So a Poset is SP if it is empty, or it can be obtained by a finite number of serial and parallel compositions from the singleton. And then a theorem by Grabowski, a Poset is SP if and only if it does not contain the N as an induced subposet. So the N is not just a Poset which we like, especially it's the moral, I mean, it's the minimal non-series parallel Poset. The equational theory of SP Posets is well understood. In particular, the generation of SP Posets from the singleton is free. So this is known since Gischer's 88 paper and the paper by Bloom and Eschig in 96. Now, the relation to concurrent Kleene algebra, let me just make the relation to concurrent monoids here. So a concurrent monoid is an ordered bimonoid with a shared unit. So you have two operations and an order. The order is compatible with the two operations, and the two operations share a unit. And in addition, it satisfies a weak interchange law, which you see here. This is easiest to explain using the interpretation, which I'm going to give in a minute, and the picture. So on the picture, you see on the right-hand side, A before C in parallel with B before D. And in particular, you notice that there are some parts of B which may be in parallel with C. Now, if you do the composition in the other order, like on the left, A parallel B composed C parallel D, then anything in B is before anything in C, so you have more ordering on the left-hand side. So this is the meaning, this is the interpretation of the ordering in the concurrent monoid, is that in the Poset or Poset interpretation, you have more ordering, which is called subsumption. So in Posets, this is called the subsumption ordering. P comes before Q if P has more order than Q. And then Gischer and Bloom and Eschig, they showed that the set of SP Posets under subsumption is the free concurrent monoid. Now, our problem is that we really like the N Poset, but it's not series parallel. And in fact, it's not only our problem, because N's are everywhere in concurrency. So for example, here there is the producer-consumer example. So on the top, you have a number of production events, which are ordered by precedence. On the bottom, you have a number of consumption events, which are again ordered. But then also any consumption can only start once the corresponding production has finished. So this is why this thing looks like this. And now if you look carefully, you will see that it's full of N's. So this example is not series parallel. It does not exist as a series parallel POM set. So we wanted to find a class of posets which includes the N and SP posets, and which has good algebraic properties, whatever that means, you will see later. So our proposal is posets with interfaces with parallel and gluing composition, as you will see now. This slide is just to wake you up and to signify that now begins the interesting part of the talk. So posets with interfaces, you see a few examples on top. So let's go through this first. The left one is just an N without interfaces. This is just a poset. But now in the next example, I have enhanced or enriched the N with a starting interface. This is the half circle, which is open to the left and which has a 1, and a terminating interface. And the idea is that in those places, I can plug other posets. I can plug other things, right? So those are interfaces for gluing composition, which we will get to in a minute. And there are two other examples, two other N's, where now all points have become interfaces. But notice that the two N's are not isomorphic, because the target the terminating interfaces are in different ordering for them. So a poset with interfaces, formally it's a poset with two injections which number some of the points. And they number some of the minimal points for the source injections and some of the maximal points for the terminating injections. So now some of the minimal points, you can declare them to be interfaces, to be plugging points. And also some of the maximal points, you can declare them to be target or terminating interfaces. So just to finish the example, you can easily convince yourself that there are 5 times 5 non-isomorphic I-posets with underlying N. So this quite enriches the structure. So intuitively, we call the image of S the starting interface, and the image of T the terminating interface, because the idea is that things which are in the terminating interface are not terminated in the current poset, but are going on across gluing compositions. They might be terminated later, right? So events in the terminating interface are unfinished. Events in the starting interface are unstarted, which we also propose to from now on be a word. It's not in the dictionary. Now, once you have those things with interfaces, you can glue them at those interfaces. So this is what the below definition does. So to glue P1 and P2 along their interfaces, you take the disjoint union of the carrier sets, and then you identify all the targets in the first with their corresponding source in the second poset, right? So you plug them together at their corresponding interfaces. And then the ordering in the result is, well, the first ordering union the second ordering union everything in the first poset, which is not a target interface, comes before everything in the second poset, which is not a source interface. So this will be easier to see using some examples. Here you see the gluings of two different ends. The first one has a terminating interface on the top right, and the second one has a starting interface top left. And then the result, you see it to the right. The big black point is the identification of the two interfaces, the gluing of the two interfaces. You see the order of the original ends in the result. Those are the red arrows, and then the black arrows are the arrow are introduced by ordering P1 in front of P2, right? Everything in P1, which is not an interface, comes before everything in P2, which is not a starting interface. Similarly, the next example, which is only there to show you that where you place the interfaces matters, right? So the only difference here is that the second end now has the interface on the bottom left, and you see as a result, those are not isomorphic even as posets. So note that gluing composition is only defined if the terminating interface of P1 is equal to the starting interface of P2, which means that you can easily see that iposets now form a small category on natural numbers as objects and with gluing as composition. Now, gluing, we also need to talk about the other composition, parallel composition. This is easier to see than gluing, but there are some differences. So parallel composition of iposets is just like for posets, put things on top of each other, put the posets in parallel, but you also have to renumber the interfaces, right? So if P1 is of type N1, M1, and P2 is of type N2, M2, then the result of the parallel composition has N1 plus N2 starting interfaces and M1 plus M2 terminating interfaces. This is an operation which is not commutative anymore. For posets, parallel composition is commutative, obviously. Here it is not. And here I show you an example why it cannot be. So what you see here is a gluing, two different gluings of, well, posets which have been swapped, right? So if you see on the left-hand side, you have the parallel composition of two very simple posets, one with 2 points, one with 1 point. And you have the two different parallel compositions. So they are symmetric, but they are not the same. And then the result of the gluing, well, they are not even isomorphic as posets anymore. Right? So gluing composition does not respect symmetries of iposets. Hence, parallel composition is not and cannot be commutative. Also, you might be thinking, okay, we had a small category on natural numbers as objects, so do we now get a prop? No, we don't get a prop, we only have a Lux tensor. Parallel composition is only a Lux tensor precisely because of the weak interchange law. If we wanted a real tensor, we would have an equality. We would need to have an equality. We would need to have a strong interchange. This would give a monoidal structure and so on, but we only have a Lux tensor. Now, gluing parallel iposets. So we want to somewhat mirror what people did with series parallel posets. The first difference is that we have 4 singletons instead of 1. Right? The singletons, they still only have 1 point. This is why they are called singletons, obviously, but the point might have no interface, or it might have a starting interface or a terminating interface. So altogether, there are 4 of them. And then recall that SP posets are generated from the first of those singletons using serial and parallel composition, and that they are freely generated as a result, and that a poset is SP if and only if it does not contain an N as an induced subposet. Now, gluing parallel iposets are generated, as I said, from the 4 singletons, and first result, this generation is almost free. So they are freely generated except for the relations which you see here. So what does it mean? It means that there's some interplay between parallel and gluing composition if the one of the component is a singleton. Right? So you see, for example, the first one, if you put P in parallel with a singleton with a target interface and Q in parallel with a singleton with a source interface, then the result is P glued with Q in parallel with the singleton, well, with the gluing of the two singletons, right? So there is some interaction here between gluings of singletons and parallel composition. Otherwise, generation is free. Now, for the second question, do we have a geometric characterization of gluing parallel iposets? Do we have forbidden substructures? Well, not quite. So what we do know is that if P is gluing parallel iposets, then there are 5 substructures which are not gluing parallel.
Well, do you hear me?
Around. And
Yes,
so,
okay, he is back.
Okay.
oh, my connection was unstable.
We lost, well, you were frozen for a while.
Okay, for a while. Should I start
Yes.
over with this slide?
Just 10-15 seconds roughly.
Yeah. Okay. Okay. I don't know where what I was
just changed the
talking about
slide.
10
You
seconds
just started
ago.
this slide and then you cut out.
Okay. Thank you. Okay. So what we do know is that if P is gluing parallel, then there are 5 substructures which it doesn't contain, which are shown on this in this proposition. The first one is a double N, and the others they can have you can give them suggestive names also. But the point is that this is not an if and only if. So we don't know if there are any further forbidden substructures, but we know that those 5 are the only posets on 6 points which are not gluing parallel, and also that any posets on fewer than 6 points are gluing parallel. So we did some more counting. You can see our results in a table here. So the first column is the number of posets on endpoints. The second column is the number of series parallel posets. Then you have gluing parallel posets. Then you have iposets, posets with interfaces. And then you have gluing parallel iposets as the last column. First thing to notice is that there are some question marks here. And that's because our counting was done using some quickly hacked Python code, which is rather slow. And obviously, if you want to count up to isomorphism, you have to decide isomorphism of posets, which is NP complete. No, it's NP hard. So yeah, we got blocked by isomorphism checking basically. Second thing to notice is something we noticed already. So there are precisely 5 posets which are not gluing parallel on 6 points. You saw them already. But note that this is still much more than series parallel posets. So not only, so the sequence P of n and GP of n only diverge at 6. And then there are not many of them which are not gluing parallel. Another thing, there is an interesting detail in the top right corner of this table. So there are 17 iposets on 2 points, but there are only 16 of them which are gluing parallel. Which one is not? It's the symmetry on 2 points. So this is the one you see here. The iposet on 2 points, which has the interfaces swapped. So it's obvious that this cannot be gluing parallel because it can only be obtained using a parallel composition. And if you do parallel composition, you renumber your interfaces consistently. So you get 1, 2, and 1, 2, right? This is why this is not gluing parallel. And last thing to notice is that, yeah, other people do counting too, especially the sequence of posets and the sequence of SP posets are well known on the online encyclopedia of integer sequences. More surprisingly, the sequence of gluing parallel posets is also well known, but under different names. So you find, if you just enter those numbers into the OEIS, it's very convenient. you find out that this is the sequence of connected, undirected graphs without induced 4 cycles, which we don't know what to do about. We also don't know whether computing GP of 7 will confirm or will confirm this coincidence, and we don't know why. So there is some work to do there. Speaking of which, let me come to the conclusion. So what you have seen is a proposal of Posets with interfaces for concurrency, which instead of a concurrent monoid gets us a small category with Lux tensor, which incidentally is also what you would call a multi-object concurrent monoid. So if there, extending concurrent monoids to multi-objects, you would precisely arrive at our notion. The gluing parallel I posets include all SP posets. They include the N. Actually, they also include all interval orders. So I didn't have time to talk about interval orders here. But it's very early that they have been recognized as being useful in concurrency. Actually, Norbert Wiener in 1914 already noted that in relativity, the ordering of events is an interval order. And then they have been taken up in concurrency theory by Leslie Lamport and Rob van Glabeck and Walter Vogler and Janicki and other people. You've seen that generation of GP posets is almost free. And you've seen the easy half of a characterization by forbidden substructures. So except for the second half of this characterization, what else are we working on? What else do we want to do with this? There are some things to do in concurrent clean algebra. So concurrent monoids give rise to concurrent semirings. Our multi-object concurrent monoids embed into something which should be bicategories with Lux tensors. So that's something we need to write up precisely. We don't know what to do with the stars of concurrent clean algebra. We believe there is a relation to Christian Johansson's synchronous linear algebra, but this needs to be worked out. Relation to Bernhard's talk, there is a notion, people have tried to do concurrent linear algebra with tests and concurrent linear algebra with domain. People have not been very successful in this. We have an obvious notion of domain where the domain elements are structureless hyposets. So sets of those, you can complement them, they are sub-identities, and this embeds nicely into the notion of semirings with anti-domains and semirings with domains. Once you have this, you can do modal constructions. So you can do some modal logic inside your concurrent linear algebra with domain. And for example, so one interesting question is, how does this relate to the higher dimensional modal logic, which was also introduced by Christian Johansson? And how does it relate to notions of higher dimensional modal linear algebra, which is something that Georg Struth is working on with some of our PhD students in Paris. Now, you've also seen higher dimensional automata, and together with Krzysztof Ziemianski, we are working on languages of higher dimensional automata. We know already that languages of higher dimensional automata are sets of interval orders. We know that concatenation of HDA corresponds to gluing of sets of interval orders. So this is what you have seen in the examples, actually. What we would like to do eventually, and we are not there yet, is a theory of regular languages for concurrency. So this is one of the main motivations for all this work, is that the theory of regular and rational languages is a rather successful thing in computer science, and we feel that it's missing. There is no such thing for concurrency, and this is something we would like to work on. Thank you.
Okay, let's applaud the speaker. Questions? Peter?
Yeah, I have a question. The Posets with interfaces reminds me a bit of people in in applied category theory are looking at things like open Petri nets. And so this is similar in the sense that you're selecting some points in the poset, and then you have input points and you have output points creating these interfaces. So has this been looked at, what the exact relationship is to this notion of open?
So there are also other relatives of this notion. So there is what are they called? I always forget their name. There's a very nice book on algebraic graph theory. Is it Coccinelle? No, it's Courcelle and Engelfried, which define an algebra on graphs with interfaces. But the difference is always that you don't impose an ordering of the first one before the second one. So open Petri nets, also you can plug them, but there is no notion of partial ordering between the first component and the second component. Yes. And the same thing with the Courcelle-Engelfried graph orderings. Also my colleague Samuel Mimram, he has a notion of graphs which can be composed using source and target interfaces, but also this has no induced ordering of left to right. So this is how we differ from those things.
And Georg?
Yeah, just further to Peter Gibson's question. So there's indeed a strong connection. I think you are referring to the categories for Petri nets by John Bass.
Yep.
Yes.
Yeah, exactly. And also I wanted to mention, I mean, Uli's remark about concurrent linear algebras with tests. So I do think that Paul Brunet, who is here today, he's found a quite successful approach with this course.
Yes, that's right. Yeah, yeah. Mm-hmm.
Other questions?
I think Daniela has raised.
Yeah, I used the Zoom feature. And so I just had a question about this future work on the regular languages for concurrency. I mean, for regular languages, we also have monoids, we have MSO, and how far has been this developed? I mean, or is there any work? I mean, apart from the HDA recognition approach?
So obviously that's something which people have been looking at before, right? Mm-hmm. But it's my impression that people have been hindered by the lack of good automata models. So right. There is some old work by Fauchon and Morin, I don't remember their first names, on regular languages for step transition systems. Which it seems they have abandoned after 2009 because it didn't get them anywhere. And there's also, there is some old work on MSO in concurrency, but I think what people have been really missing are good automata models. And I happen to believe that higher dimensional automata are a good automaton model for concurrency.
Okay, thank you.
Welcome.
Are there other questions?
Not a question, but a remark. Mm-hmm. Kleene algebra, at least one of the interface models, they form a Kleene module. And so you can have domain in that sense. So that has been done some years ago.
Okay, you have a reference for this? We'll probably
MPC 2015.
Okay, thank you.
Other questions, remarks? If not, let's applaud Uli and also Bernhard for their talks.